Okay, let's get started. The next speaker is Ed Stephenson.
Mike, it's on.
Yes.
And you're recording? Recording. Okay, so pointer in the right hand, advanced clicker in the left. I want to thank all of the organizers of this meeting for their beautiful work in putting everything together and in collecting a really outstanding set of speakers. This has been a pleasure to come back to Madison, Wisconsin, see the campus in its present glory, and to have a chance to meet and chat with so many of you. I also want to thank the organizers for inviting me. I don't understand exactly why, but probably because I'm part of the Willy Haeberli family of students. But the topic that I'm going to be talking about here doesn't really overlap with Willy, nor did I ever talk with him about it. So in that sense, we're pretty far down the food chain here. And my last thank you goes to Frank Rathman, who succeeded in showing most of what I have in my talk. So what I'm going to do here is to relax a little bit, maybe take a few more minutes on the things that are still unique, expand on it. And when you see something that looks like something you just saw, we'll skip on through that to the next thing. So my involvement with this whole storage ring project started a long time ago. I got a call from Bill Morse. Bill Morse is in high energy physics at Brookhaven National Lab. And somewhere in 1999, I don't remember exactly when, he called me up and he said, we've been talking about this storage ring experiment, and we're looking for somebody who understands spin 1. Do you know anything about that? Apparently, through some 2 or 3 step process, he had gotten hold of my name as somebody who might understand how to talk about the polarization of a deuteron and a deuteron beam. So that encouraged me enough that I went out to Brookhaven, and there I gave a talk about vector and tensor analyzing powers and polarizations and how one does all of this with the polarized ion source and so forth. That took me the whole hour. And in the process in that trip, they told me about the idea of the storage ring experiment to look for an electric dipole moment. So that was my first introduction to it. Let me just share a few clips and inserts from where we are now. Again, thanks to Frank, I can skip most of the summary. That's covered up here in the very first part. EDMs violate C and P symmetry. He did a nice job on that. They're expected in the standard model to not appear before something like 10 to the minus 31 e centimeters. And now you've been introduced to that, so you know all about it. But the idea, and the reason I picked this particular graphic here, is that I lifted this out of a talk from Yannis Samartzidis. And Yannis is the fellow in Brookhaven who had been working on the idea already in 1999 for a number of years, was enthusiastic about it, and that's a word that describes Yannis to the core. And he was already planning to pursue this project for the rest of his life. Anyway, so you know all about the implications of EDMs for matter and antimatter and other such interesting and important results. So the idea came out of the G-2 experiment, and the reason this picture's here is because it shows you the G-2 ring. And what happens in the G-2 ring is you're trying to make a precise measurement of the magnetic moment of the muon, because you know the magnetic field in the ring very precisely. Basically, you're calibrating it against the proton magnetic moment. And so you count the number of revolutions that the muons make as they go around the ring. by watching their decay. That decay is parity violating. There are a bunch of detectors around the inside of the ring. They pick up the muon decay, and by looking at the oscillations in that, you can learn about the muon's magnetic moment. The reason that this came up is because one of the systematic errors in that experiment is what happens if the muon has an electric dipole moment. So people looked into this and discovered that that would bring the spin out of the plane if that were to happen. So that turned out to be one possible systematic. And so they could look at the detectors which had vertical sensitivity and determine whether or not that systematic was appearing and might have an implication for the muon's magnetic moment. It didn't, but that was the germ of the idea. Yanni said, well, how can we change this around so that we are sensitive to the electric dipole moment in first order? And that was the birth of this idea. So this particular page comes out of the snowmass process. Yannis has already submitted this whole thing to consideration for high energy physics priority. We'll see how that goes over the next few months to a year's time. But the hype is already here. Largest spinning trap in the world. G-2 reached 3 billion people. I think that's the reach of television is what that is. And the G-2 experiments are used to plan the next generation of high precision physics experiments. So he's already saying that this is the beginning of a new domain of experimentation based upon high precision and high sensitivity. You've already seen this. That's the same drawing that appeared in Frank's talk, except for the addition of a polarimeter. I thought that would actually help. So this shows you the idea of putting the spin of the particle in plane, letting it go around the ring. If it's frozen, then it stays oriented parallel in a vertical sense to the velocity. And then what you do is you look for the slow rotation of the spin out of the plane due to the electric field. So there's always an electric field here. And in the current version of the storage ring experiment, this electric field is generated by electric field plates. So it becomes a pure electrostatic machine, and that generates a torque which rotates the polarization. This is the torque equation, the EDM force, and gives rise to this change in the spin direction. And that all depends upon this combination of electric and magnetic fields. So you can do this also with a magnetic field. It's the same field that would generate an effective electric field pointed towards the center of this ring. And if you think about it, you realize that this is in fact the electric field that closes the orbit for the experiment. So in this particular situation, the reason Bill Morse called me up was because these guys depended on beta decay to measure polarization. And they were faced in this idea with a hadron that might be spin polarized. So how do you do that? So this has to do with culture, and it has to do with history and what you learn in class and all these kinds of things. So, you know, what is second nature to me, because I'm part of the Willy family of students, is that all of this was ground into me from the very beginning. And so here is our answer to the diagram for the muon beta decay. And that shows that you have to come up with some sort of a pseudo vector that could carry the spin information in the scattering process. And the quickest way to do that is to do a Kn cross K out for the particles coming in and doing something like elastic scattering. And the cross product of those two vectors produces a pseudo vector along the y-axis. So that is where your polarization sensitivity starts. And so we, of course, describe this by doing the cross section given by the product of the polarization times the analyzing power. Cosine phi simply says that as you go around this azimuth here, with your spin direction, then it has a cosine variation. So what you want to do with this polarimeter is to come up with some process where A is very big so that you have a big effect. And so it was obvious that elastic scattering was going to be the primary candidate for this. So here, for example, is deuteron carbon elastic scattering at 270 MeV, measured in Japan. And this is the analyzing power, goes from about 20% up to nearly 1 within a region where the cross-section is also very large. And what that does is it generates a very large figure of merit for the experiment. This is the peak of that figure of merit, sine theta sigma times the square of the analyzing power. And this is your statistical sensitivity to the polarization of the beam. So this is where you need to build the polarimeter to operate well. Anything outside this red line to larger angles, even though the analyzing power gets bigger, is of no direct use. So this was the idea behind the experiment. And please note that at this point, I'm still using the deuteron. Again, a historical fill-in here. Back when this was going on, when Bill called me, the deuteron was the candidate for doing the storage ring experiment because they expected an interesting effect to arise from the G-2. See, there's this disagreement between experiment and standard model, which still persists unless you happen to believe that the lattice calculations will bridge this gap. We have yet to see whether that's possible. But this difference was going to appear in the pion exchange between the neutron and the proton inside the deuteron, therefore giving the deuteron considerable edge in having an electric dipole moment. So that was the reason the deuteron came up in the first place. So the question is, how do you do things with deuterons? And that was my purpose in going to Brookhaven in '99. This is just a little thing to explain frozen spin. You've seen that already. I will repeat for you something that Frank also showed differently. And that is that in order to do the experiment, you have to meet a certain number of requirements. And so one of the ways to define that is to look at the error on the measurement, see what it depends on, and then figure out what you know about all of these inputs into the equation. Here's a list of what we think now might be possible for those various inputs. But as you look at this list, what you realize is that some of them could potentially be very problematic or hard to reach. So at the time that these lists were created, by the way, if anyone is curious about systematics, go dig up that reference. Newly published work from Omarov. He's working in South Korea now, which covers all of the systematics in the experiment. I'm not going to touch on this, but that paper does. You have to achieve all of these things, and particularly worrisome is the fraction 1%. That means that if you really want to try to get your statistics built up in a reasonably short time, meaning a year or two, then you have to have extremely high efficiency in the polarimeter. So that means that of the particles that are lost from the beam, 1% of those must appear in the detector in a way that is useful for making a polarization measurement. That is barely on the edge of possibility. If you go back to this cross-section graph here, you really have to get 1% of all these guys into your detector. But one of the problems with storage ring experiments is that you use thin targets. And so this becomes an issue. Frank briefly alluded to the solution to it as we have it now. I'll comment on that in a moment. Other things that were problems at the time that this started was the very long lifetime of the polarization in the horizontal plane in the ring. It's subject to spin decoherence, and that needs to be addressed. So all of these things here have to be addressed. And at the time, we were just having meetings, systematic errors. Is frozen spin really possible? All those kinds of questions were coming up. And we were just having meetings in Brookhaven. So I found this situation over time frustrating. I'd finished with a charge symmetry experiment and was looking around for what might come next. So I started working with the folks at KVI in Groningen for a bit of time on measuring some deuteron carbon angular distributions so that we would know where the analyzing powers were large. But then it became clear that we needed to do something beyond that to address these issues. And I wound up visiting Jülich in 2005. It was my first introduction to the machine. I was very impressed with it and realized that I could do something with it. So in 2007, we submitted a proposal to the Jülich Program Committee to begin a series of studies on dealing with the systematic problems associated with storage ring EDM. So we've took the first data in 2008 and 2009 on polarimetry related issues. I'll cover that in a bit of detail here. It turns out that Frank alluded to putting a thick block target into the ring. And here's how the thick block target actually works. This was an early version, oops, wrong button. This is an early version of it here, which we later abandoned, but it was a way to get started. The process is, as far as we can tell, two-step. If you have this at the edge of a beam and the beam is coming along below it, then there will be some edge of the beam which comes up and barely touches the underside of the carbon block. And you can encourage this by putting a bit of white noise on some vertical electrostatic plates in the ring that jiggles the beam. You can do it on some harmonic of the tune of the beam, and then you will begin to bring some particles out of the beam. Sooner or later, somebody's going to hit the bottom of this thing, and there are all sorts of lumps there. And it gets a little kick so that it now comes around and comes out at a different place. So this begins an oscillation which is vertical and goes on. The tune of the ring, which is the number of those oscillations per revolution around the ring, is 3.6. And what happens is that it comes out and it hits this target front on. And so this has to be a significant distance. We measured that to be about 0.2 millimeters. That's enough to allow for the spread from multiple scattering inside the target. So you really sample the whole target thickness. This is crucial for efficiency. And so you can, in fact, achieve 1% by doing this trick. So that's one piece of progress. The next thing I want to mention about this particular set of studies that we did is that we wanted to look into the question of polarimetry measurements. If you're doing things that involve comparing scattering to the left and scattering to the right, you are very geometry sensitive. And so if the beam moves a little bit to the left, you'll favor the left side. If the beam steers a little bit to the left, you favor the left side, and you destroy the neat asymmetry that's necessary for measuring polarization. And in particular, if those changes are slow and continuous with time, it can mimic an EDM. What I just described to you is the EDM signal. So there are all sorts of tricks that we polarization types have in our hip pocket for dealing with these things. You do both sides of the beam, so you have detectors left and right. And you also flip the spin, so you have spin up and spin down. You put together these nice combinations, and your product P times A drops out. And these things tend to suppress all sorts of first order systematics. Okay, first order systematics are great. It buys you about down to the 1% level. And then things start to crumble underneath your feet. So you think about the sensitivity that you need in making this polarization change measurement to see the EDM. And you're going to wind up, if you can hold the beam in the machine for about half an hour, with something like a micro radian of tilt. That's 10 to the minus 6. So that's going to be hard to reach. So how do we do better? One of the things that we tried was to take a look at this stuff and see if there were other combinations that would be useful. This combination here, where you put left, left over right, right, and calculate something that looks like the P times A up there, is an interesting quantity because it suppresses polarization and emphasizes systematic errors. And so you stick this in the formula where you take your first term here and you create this as a correction term times delta phi, and also rate effects. I'm going to go through the end of this really fast because it's duplicates. You do rate effects here, and those then can be modifications to the symmetry. There are all sorts of inputs to this. Angular distribution effects, polarization effects, various things. Then you go off and you measure various polarization observables. You do angle errors, you do position errors. You look at how these things shift, what happens as a function of the error, and you can come up with all sorts of slopes and things which connect back to the inputs, and you can really measure the properties of this sort of error system in fairly complete ways. So given this, here's what you can, in fact, achieve. So one of the tests that we used at the end was that we decided we would spend 4 days measuring the beam polarization continuously, because that would give us reasonable statistics. And we set up a cycle that lasted for about a minute. And the uncorrected data is the red stuff. And this particular shape that emerged is the signature of the extraction efficiency as we were doing it at the time. So that's a count rate effect. And if you've measured that as a part of everything else, you can take it out. So here is the count rate mostly removed. That's the blue dots. Now, if you apply all the geometry stuff, you get to the black dots. And if you look at that, that is flat to part and 10 to the 5th. Other things that Frank talked about, measuring the horizontal polarization by looking at the various bits of things, by doing up and down scattering. You get a lot of information out of those runs. Here's the full spread of beam around the ring. Electron cooling narrows it to a peak. You then turn on your polarimeter stuff. You make measurements. And then with the polarization in plane, you can make measurements of the lifetime of the polarization. Here are some reasonable polarization lifetimes and some not terribly usable ones. What makes the difference is the way you tune the sextupole fields of the machine. So here we have a bunch of sextupoles, 5 of them, that are mounted around each of the arcs in the ring. You make adjustments to those, and you can tune out the effects. What you're trying to do, what feeds that effect, is the fact that as you allow betatron oscillations, you increase the length of the orbit because the orbit period is fixed by the RF. But in order to make that work right, gamma has to be unchanged for the beam. So what you have to do is you have to shorten the orbit. And if you have mixed sextupole and quadrupole fields, you can take orbits that have a large betatron oscillation and move them relative to orbits with low betatron oscillation. You can move them to a lower radius, and this allows you to actually make a correction that removes the distortions that give rise to depolarization. So here are some views of the chromaticity, which is also connected to this adjustment. We're looking for places where chromaticity is 0. These are X and Y plane chromaticities as a function of some of these sextupole magnet fields. And so we want to try to measure along that diagonal. Here are lifetimes measured along that diagonal. Again, axis here and here for 2 of the horizontal plane adjustments in the sextupole fields. And what you discover is that along that 0 line, there is an optimum setting for the system, and that's what gives you the long lifetime. So we come back to this plot that Frank showed you earlier this morning of the 1,000-second lifetime that we were finally able to achieve. Frank showed you that. And so this brings me to this particular picture. So let me spend a few minutes on it because Frank unknowingly promised you that I would talk about this. It turns out that there's an interesting trick you can pull. If the electric dipole moment is oscillating and you are trying with a beam that rotates in the plane to create a vertical precession with that, then if you can figure out what is the frequency associated with the axion field, this is a feature of its mass. And if you can match that with the spin-tuned frequency in the machine, you can create a resonance. You can get both of those rotating at the same frequency. Then the spin will accumulate, even though it's not a frozen spin experiment, because it will go up here, but then it runs around over there. But, you know, I'm doing an oscillating field, so it also goes up. And you can accumulate this over and over again. This is a model calculation of the accumulation. If you're doing a scan in frequency through it, you can actually do a kick and go from one polarization in the beam to another. We generated a sample test with that using the Wien filter that Frank described. Here's a test. This is what a fake axion would look like. And you can do these various fits to it to try to pick out places of sensitivity where you might have been able to do a measurement. So here on the right-hand side of the picture is the results of the very first demonstration that this stuff is feasible. And so what we have is the sensitivity limit at the 90% level for a scan that goes from 120 up to 121.4 kilohertz. So those are frequencies associated with the mass of the axion. It's not a very large range. This was just a demonstration project to show what's possible. And this is about 100 different runs of scanning, each one a tiny little step. And so the limit here turns out to be around 6 times 10 to the minus 23 centimeters. So this is a relatively systematic error-free experiment because you're looking for a frequency. And frequencies are hard to fake, especially if it's an oddball frequency that doesn't come in anywhere else. So this is essentially systematic error-free at this point. The only thing that limits this number right now is running time and patience with the scan. If you scan more slowly, you can bring the level down. If you use more beam, you can bring the level down. The question is how much time you should spend on that, searching through frequency space, because frequency space is pretty darn large. Many orders of magnitude need to be covered. Okay, so in all of these studies, we addressed thick targets, in-plane polarization, polarimeter feedback, higher order corrections for polarization lifetime, scanning to search for axion-like particles. So the interesting thing about all of these things is that whatever we tried, we eventually were able to solve. And I regard this as a tremendous point of encouragement about going on with this field of high precision measurements and high sensitivity studies. Maybe we can really do this. Thank you.
Thank you very much, Ed, for an interesting talk. I'm sure there are questions.
Yeah, right time for the picture. Right?
Yeah.
Questions?
Steve Victor.
Just a comment. I wanted to comment on how things got modified from a Deuteron EDM search to a proton EDM
Oh, please,
search.
because these things diverge. We started working with the Deuteron at
Right.
COSY and stuck with it because we knew what we were doing. And now the scheme is for protons.
Right. So this happened at Brookhaven when I was the associate director there. And, you know, when I came in, Giannis came to me with this idea. There were many competing ideas. And I told him, you know, you'll have to get significant amount of funding to do this. We discussed the details of the experiment. I was quite worried about, you know, a fundamental systematic limit coming from magnetic fields, which were essential to do the Deuteron EDM. I was also worried that, you know, the initial interpretation of a Deuteron EDM was going to, you know, be, worried about the effects of the Deuteron wave function, and the, you know, and that the proton EDM would be easier to interpret if one measured it, and one could do it with, in principle at least, with a purely electrostatic machine with counter-rotating beams. So, you know, when it came to actually writing a proposal, which Giannis did, you know, for the DOE, we just thought, and we also had review committees that, you know, that had similar impressions, that it would be easier to sell the idea of an ultimate experiment, which was proton EDM in an electrostatic ring.
Yeah, that happened around 2009 or so. And so by that time, we were already 2 years committed to doing Deuteron beam stuff, and we're at the point of just starting the systematic studies of the beam handling and tuning capabilities of COSY. So we decided we'd stick with it, thinking that whatever we learned would be useful.
Other questions?
I think these people want to go get their picture made.
Exactly, and lunch. So let's thank Ed again.